On the 26th of September 2022, a 570-kilogram spacecraft the size of a refrigerator rammed into an asteroid at 6 kilometers per second. Launched aboard the fossil-fueled powered Falcon 9, the dinosaurs finally clapped back. 66 million years after the asteroid that ended the dinosaurs, an unsuspecting asteroid was struck with an impact equivalent of 3 tons of TNT, and we caught it all on film. This mission is perhaps the most important experiment NASA has ever performed. Data and information that could one day save us from the same fate as the dinosaurs. The asteroid we struck, Dimorphos, is 160 meters in diameter, much smaller than the 10-kilometer wide asteroid that exterminated the dinosaurs all those years ago, but large enough to unleash over 300 megatons of energy if it collided with Earth. 6 times more powerful than the most powerful nuclear weapon ever used. In the weeks since, scientists have been studying the results, calculating how effective our first asteroid redirection test was. However, the work that went into this mission far extends the last month of scientific study. For years, scientists and engineers carefully planned which asteroid to hit, how to hit it, and how to confidently and quickly measure the effect of the collision. To understand the achievement of the DART mission, let's dive into the engineering and physics of its planet defense mission. The DART spacecraft itself hosted no scientific instruments, designed to be a low-cost spacecraft with just the tools it needed to complete its mission. Cameras to spot its target, star trackers to navigate through space, a propulsion system to direct it toward its target, antenna systems to speak with Earth, and an onboard computer, whose software has its roots in military missile technologies. However, DART did release a small Italian-made spacecraft designed to record the collision, giving us this footage showing a massive plume of debris being ejected from the asteroid on impact. The Falcon 9 rocket did the majority of the work in directing DART toward its target, Dimorphos. This was a unique target, chosen for a very important reason. It's a moonlet, a tiny moon orbiting the larger asteroid, Didymos. DART's camera gave us a glimpse of Didymos as it sailed by at a breakneck speed, closing down the remaining 920 kilometers in just 2.5 minutes. It computed and adjusted its trajectory using hydrazine thrusters, guiding the spacecraft to a head-on impact with the moonlet. In these final moments, DART shut down its thrusters, allowing the camera to take clear images of its impending doom, and giving us a clear picture of the rock we just obliterated 11 million kilometers away. So, why this rock in particular? There are countless asteroids orbiting the Sun. However, in order to study the results of impact, we need a specific kind of asteroid. First, Dimorphos was passing close to Earth, passing by at 11 million kilometers at the time of impact. We have tracked Dimorphos and have confident predictions of where the asteroid is going to be at any given point in time. This allowed us to choose an optimal window for collision. Our model showed that on October 4th, 2022, the asteroid would be at its closest approach for the next 40 years. The next time it would be this close to Earth would be 2062. This was the perfect opportunity. However, we struck it a week early because the asteroid would be at its brightest to us at its closest approach, allowing us to better observe the results of the collision. This is the next reason this asteroid was chosen. The goal of the double asteroid redirection test was to redirect an asteroid with just enough force to change its trajectory by a marginal amount, enough to avoid a collision with Earth. A change of just 1% could be enough to avoid a catastrophe. But here lies the dilemma for scientists. How do we measure such a small change in trajectory of an object 11 million kilometers away? Even the footage from a spacecraft near the collision is not much to go off. Confidently measuring an impact with an asteroid orbiting the Sun would take years, as we'd need to measure multiple orbits to assess the differences before and after the impact. Instead, scientists turned to binary systems for answers. There are systems of asteroids where one smaller moonlet orbits a larger asteroid. All we need to know is that we changed the velocity of a moving rock in space. It doesn't matter if it's orbiting the Sun or orbiting another rock. However, not any binary system would make this experiment feasible. It is essential that we can measure the effectiveness of the crash from Earth. For this, the orbiting moonlet should have an eclipsing path, meaning that viewed from Earth, it would pass in front of and behind the asteroid during its orbit. The light reflecting from these two asteroids that we see here on Earth appears as a single point of light, and each time Dimorphos passes in front of Didymos, that light dims. Using sensitive Earth-based telescopes, we have timed these patterns to measure the orbit of Dimorphos at 11 hours, 55 minutes. Using these same techniques, we can measure the change in orbit. Dimorphos is only visible from the southern hemisphere, so NASA reserved time on telescopes located in Chile, South Africa, Australia, and New Zealand. Joining the Earth-based telescopes, Webb and Hubble were also used to image the asteroids at the time of impact. Of course, to achieve all this, we first needed to hit the asteroid. That was no easy feat. The asteroid was too far away to manually direct the spacecraft. There would be a lag of 1.5 minutes. At 6 kilometers per second, a lag this large would have the spacecraft travel over 540 kilometers before receiving instructions. When trying to hit a target only 160 meters in diameter, lags like this required an autonomous navigation system. The spacecraft was loaded with a camera attached to a small 20 centimeter wide telescope, and circuitry no more powerful than that of a PlayStation 1. Every second, it would take a picture and calculate the thrust needed to stay on course, working very similarly to visual guidance software used in military applications like the Javelin missile. DART used 12 directional thrusters to hit the small dim moonlet. DART was also equipped with the next generation of ion thrusters, NEXT-C, which is 3 times more powerful than NASA's previous generation ion thruster, NSTAR. Ion thrusters are highly efficient, accelerating heavy ions of xenon to extreme speeds of 40 kilometers per second using an electromagnetic field, 10 times faster than a traditional rocket engine. These ion thrusters were powered by new, specially developed lightweight solar cells that deploy from a roll, called a Roll-Out Solar Array, or ROSA. This solar array was successfully tested on the ISS in 2017, although in a strangely hilarious video, the arrays were gently ejected from the ISS because there was a fault in retracting them at the end of the test. Part of the solar array was also used to demonstrate a new solar collector technology that would concentrate sunlight on high-efficiency panels, increasing their power deep in our solar system, where solar radiation rapidly drops off thanks to the inverse square law. A technology that would be extremely useful for powering an ion thruster, allowing us to reach asteroids further from Earth and giving us a better chance of changing their trajectory early. These systems were successfully tested on DART. However, Ed Reynolds, the DART program manager at APL, revealed in a post-impact briefing that the NEXT-C thruster was actually only tested for a short 2-hour period during flight. An unexpected issue arose that could have caused 100 amps of current to run through the thruster, which it had not been tested to withstand, forcing the team to make a decision to not continue testing the thruster, instead relying completely on the hydrazine thrusters to focus on the primary asteroid redirect mission. And while this is disappointing, finding a new issue is an important part of the testing process, and it didn't impact the mission at all. The mission itself was a massive success. After just 2 weeks of gathering data, NASA announced on October 10th the effects of the collision. Striking only 17 meters from the asteroid's center, DART practically struck the bullseye. Not just changing its orbit by 1%, but by a relatively massive 4.5%, reducing its orbit around Didymos by 32 whole minutes, down from 11 hours 55 minutes to 11 hours 23 minutes. This is a mission worth celebrating. We are now confident we can deflect an asteroid like Dimorphos if the need arises. Beyond moon missions, beyond Mars missions, beyond all the understanding NASA and other space agencies provide us, this mission has clear, understandable importance. We now have data and tools in our arsenal to protect our planet. We are now a little safer on this little rock floating through the vast, mysterious expanse of space. This mission was primarily designed to gather data on how a collision like this would affect the orbit of an asteroid. There were many questions to be answered about the geological composition of the asteroid and how that would affect the transfer of momentum from DART to Dimorphos, especially as most asteroids of this size are simply piles of rubble that have coalesced due to gravity over time and aren't a single solid mass, making exact predictions on the collision physics and how the orbit would be affected very difficult. Basic calculations of gravitational physics are pretty easy to learn, however, and understanding them gives you all sorts of fun powers, unlocking the knowledge of space travel and planetary motion. You can learn more about that by taking this course on Brilliant, and when you are done, you can move over to our very own Real Engineering course. All this is available to you by signing up to Brilliant's free trial with the link in the description. And if you found value in the math and science courses you took for free, and I'm sure you will, you can continue with 20% off the annual premium subscription. This offer is only available to the first 500 people to sign up. Our in-depth interactive course teaches you about the physics of orbit and traditional rocket launches before teaching you about the fundamentals of kinetic launch systems. A course designed to help you understand spin launch, the subject of our recent documentary. You can get access to that course right now and all of Brilliant's other curated interactive courses by clicking the link in the description. A fantastic course to start is Computer Science Fundamentals, the perfect course for high school or college students starting their journey on computer science. This course will teach you core computer science concepts, and when you are done, you can move on to more advanced courses like programming with Python. Brilliant teaches with interesting and fun interactive courses that challenge you along the way, making the learning process much easier and more rewarding. And they're adding content monthly, so there's always something new to learn. You can get started for free by clicking the link on screen right now, and the first 500 people to do so will get 20% off Brilliant's annual premium subscription.